Okay, so let's start. Yeah.
Okay. Yeah. Thanks, Vanya,
Okay.
for this invitation. It is a pleasure to be after so many years again in Edinburgh.
Yeah. Okay. We're not in Edinburgh. We're worldwide. This is a worldwide.
Even to be on the world again is very nice. It's a good place.
Okay. So let me introduce. It's my big pleasure to introduce Juergen Hausen from Tübingen, and Juergen will speak about the automorphism group of rational projective surfaces with cis direction.
Okay, thanks again, Vanya. I should say this is joint work with Timo Hummel, who is also visiting the seminar. And I begin with some very basics because just it's not so clear to me how much do you know about C-star surfaces. In this talk, a C-star surface means a normal projective complex surface X with an effective action of the multiplicative group C star, a morphical action, and the action T applied to X is just denoted as T dot X. Let us have a look at some very basic but instructive examples. C star actions on the projective plane. In this picture, we see the projective plane represented by the triangle of its coordinate axis. And the C star action is given in homogeneous coordinates by T dot Z equal Z naught TZ 1 T squared Z2. In this picture, these arrows indicate what happens with T dot X if T goes to infinity. As C star acts on a complete variety, we always have the two limit points for T goes to 0 and T goes to infinity. And for instance, in the picture above, if you look at the point 1, 0, 0 and 0, 1, 0, and you take the point with coordinates 1, 1, then the limit to 0 is 1, 0, 0, and the limit for T going to infinity is 0, 1, 0. Another action on the same variety, again on the plane, is given by T dot Z equal Z naught Z1 T Z2. Another behavior of the action: in the first case, we have 3 isolated fixed points. In the second case, we have a curve of fixed points. That is this thickly drawn coordinate line, and we have 1 isolated fixed point. A fourth example is the action on P1 times P1 fiberwise, where we have 2 curves of fixed points. We've already seen all possible types of fixed points of a C-star surfaces. There are 3 types: elliptic, parabolic, hyperbolic. It's called elliptic if the fixed point is in the closure of infinitely many non-trivial C-star orbits. It's called parabolic if it's in the closure of exactly 1 non-trivial C-star orbit, and it's called hyperbolic if it's contained in the closure of exactly 2 non-trivial orbits. It's already a nice exercise to show that for any normal C-star surface, there are only these 3 types of fixed points. So if you look in the examples, go to the action on the plane, the one on the left-hand side. There we have 2 elliptic fixed points, namely 1, 0, 0 and 0, 0, 1, and 1 hyperbolic fixed points, namely 0, 1, 0. Then, for instance, in the case of C-star acting on P1 times P1 fiberwise, we have 2 curves consisting of parabolic fixed points. These parabolic fixed points, they always show up in a curve. For a C-star action on a projective surface, there is always a source and a sink. That means connected components F plus and F minus of the fixed point set that admit open neighborhoods u plus and u minus respectively, such that for all points in u plus, the limit t dot x for t to 0 lands in the source f plus, and similar with the sink for all points in u minus, the limit t dot x for t goes to infinity lands in the sink f minus. So in our pictures, the C-star action on the plane left-hand side, the source consists of 1 point, 1, 0, 0, an elliptic fixed point. The sink, also one elliptic fixed point. The C-star action on the plane on the right-hand side, the source is a curve of parabolic fixed points, and the sink is a single elliptic fixed point. So these are some very basics. Now let us turn to the state of matters in the 70s. This is basically work of Orlik and Wagereich. I'm reporting on 2 papers, one of them appearing in the Annals of Mathematics and the other in Acta Mathematica. That means that the 70s were a golden time of C-star surfaces. Here's the general picture. F plus is our source. This can be a single elliptic fixed point, or it can be a curve of parabolic fixed point. And then on the bottom, we have the sink. The general orbit connects source and sink and has trivial isotropy group. Besides the general orbits, we have these arms. They are in general unions of several rational curves. On the left-hand side, we have one such arm starting with D01 up to D0N0. The number of members can vary from arm to arm. Also, the isotropy groups inside the arms can be of, no, this is something which I want to say later. In the intersection of 2 such arms, we find always a hyperbolic fixed point. The sink, again, is elliptic fixed point, or it is a curve of parabolic fixed points. Now here's one of the theorems of Orlik and Wagereich. Suppose that X is smooth and the source as well as the sink of the actions are both curves. Then the genus of these 2 curves, which is in fact one and the same, so they are of the same genus, together with the self-intersection numbers of these curves and the self-intersection numbers of all the curves in the arms, these data fix the topology of X. Moreover, there are some statements, some nice statements in terms of continued fractions. If we look at the curves inside one arm, say the ith arm, then if I take the continued fraction over minus the self-intersection numbers, this gives us 0. Moreover, if I take the self-intersection numbers up to the penultimate of the arm and call this 1 over Ci, then I get a nice identity between minus d plus square minus d minus plus square equals the sum of these numbers CR. This is a statement in one of the big papers of Orlik and Wagereich. They also took care about the singularities of a C-star surface. Recall that we have only normal surfaces. That means all singularities are isolated and then they are necessarily fixed points. The parabolic and hyperbolic fixed points, they are at most cyclic quotient singularities. That means they are resolved by chains of rational curves. And we call such a point X quasi-smooth. That means if it is a cyclic quotient singularity. So hyperbolic and parabolic fixed points are at the most cyclic quotient singularities. The picture is more interesting if you go to the elliptic fixed points. Oleg and Wackreich have shown that they have such star-shaped resolution graph. And these elliptic fixed points, they are precisely the weighted homogeneous surface singularities. So this is a quite famous and well-studied class of singularities. Another thing due to Oleg and Wackreich is a so-called canonical resolution of a singularity. It shows up in this commutative diagram. Here, let us start to discuss it from the right-hand side. On the very right-hand side, we have the field of invariant rational functions of X. And this corresponds to a projective, smooth projective curve Y. Then we have a rational map from X to Y induced by the inclusion of function fields. And if we resolve this in a minimal way, the indeterminacies of this rational map, then we get a variety X prime dominating X, and from X prime we have an honest map, an honest morphism onto Y. Then we take the minimal resolution of this X prime, that's our X double prime. This is what Oleg and Wackreich call the canonical resolution, and this will show up later as well. This canonical resolution is in general not the minimal resolution. For the minimal resolution, we have to contract -1 curves, exceptional -1 curves in the fiber. So what this map from X prime to X does is that it replaces possible elliptic fixed points with parabolic fixed point curves. All the morphisms in this diagram are equivariant with respect to these directions. That have been the results from the 70s, and they are enough to formulate the statement on the automorphism group, which I would like to present. More specifically, we give a statement about the unit component of the automorphism group of a rational C-star surface X. If you have a rational surface, then the automorphism group is a linear algebraic group. And that maybe makes it particularly interesting. And we are going to determine this automorphism group, at least its unit component, in terms of data of X, geometric data, namely self-intersection numbers and certain intersection numbers of these invariant curves from the arms, and some orders of isotropic groups. So we look at the minimal resolution of X, C-star equivariant minimal resolution. And now I distinguish two situations. First, assume that we have a parabolic source in X, D+, and we denote by xi the unique point contained in the intersection of the ith arm with the source D+. Then if we do the minimal resolution, if this point is a singularity, then there is a chain of rational curves in the fiber over this point, as we have seen it. As I told you, this is a quasi-smooth point. As you have cyclic quotient singularity, so the resolution graph looks like this. We define for each xi, that means for each arm, a number ci of D+. Now we take a part of this continued fraction we have seen by Orlik and Waagreich. We only go through those curves which are in the fiber over xi. And then we take the inverse of this continued fraction. So we will need this number. In case that the point was smooth, we put this number just equal to 0. The next situation is that we have a simple elliptic fixed point, x minus in x. I have to explain what does this mean. Simple means that the resolution is in a very simple way star-shaped, namely it's just a chain. And moreover, this chain should be contained in one of the arms of the minimal resolution x tilde. And we enumerate it in such a way that the last one, EQ, hosts the elliptic fixed point of x tilde. Note that there must be an elliptic fixed point because we require the whole fiber to be in an arm. So there is no room for a parabolic fixed point curve by this definition. Again, we take this, we develop this partial continued fraction along this fiber over the singularity and define Cx minus to be the inverse of this continued fraction. Moreover, I need the orders of the general point from the curves dij lying in the arms of the C-star surfaces. These are finite cyclic subgroups of C-star, and we denote by Lij the order of these groups. By suitably renumbering the arms, we always can assume that L0, N0 is the biggest and LR, NR, the last one, is the smallest. And in case two of them are identical, then we require that the self-intersection of DI, NI is less or equal to the self-intersection of DJ, NJ. So now we have everything to state the theorem. It is the following. We look at a non-toric rational C-star surface. Then the unit component of the automorphism group is a semi-direct product of, I'm speaking first of the term in the parentheses. This is C to 0, semi-direct C to zeta, where rho is a non-negative integer and zeta can be 0 or 1, and this twisting homomorphism phi is specified later. And then we take the semi-direct product of this group with the acting group C star twisted by a homomorphism psi, which is also specified later. What about rho and zeta? They can be both 0 or exactly one of the following holds. Either we have a parabolic fixed point curve, which is without loss of generality D plus, and this parabolic fixed point curve is of non-negative self-intersection, or we have a simple elliptic fixed point, which without loss of generality is x minus in x. If we are in the first setting, then zeta equals 0, and rho is given via self-intersection numbers as follows. It's a maximum of 0, d plus square plus 1 minus the sum from I to 0 over all these numbers, ci of d plus we just defined. And the twisting homomorphism looks simple. It's just a diagonal matrix, row by row, diagonal matrix having in the diagonals t to the minus 1. More interesting if you are in the situation of a quasi-smooth simple elliptic fixed point x minus. then we can say that rho is a maximum of 0 and a number which depends on some isotropy group orders Li, Ni, and on self-intersection numbers Di, Ni square, and as well on intersection numbers between Di, Ni, and it should be, yes. So what I just want to say with this, giving this formula is that this rho, this dimension of this 0 being part of the automorphism group is completely determined by this data of the action and in this very precise way.
So, Juergen, this two cases describes when the group is reductive, yeah, when rho is 0 and Xi is 0.
This group is for surfaces only reductive.
When rho is 0, so this is 1 and 2. It basically describes when you don't have the C part. Yeah, you only have C star. Yes, correct.
Yes, I mean if both of them are 0.
Yeah. Okay.
The point is that we have a non-toric surface.
Yes.
So it's only reductive if it's equals C star.
Okay, I misunderstood. Oh, okay.
Non-toric is important here.
Okay.
So now what does it mean that this zeta equals 1? Another condition in terms of isotropic orders and intersection numbers. And what is still missing are the twisting homomorphisms. First, phi, this twisting homomorphism inside the parentheses. Then we can write down the defining matrix of this homomorphism. It's a diagonal, it's a trigonal, unipotent triangular matrix, and some terms using binomial coefficients are in the upper triangle, as it is written here. Yeah, this is just to say that also this twisting homomorphism is completely determined. And then the psi is as well completely determined, again by a diagonal matrix. And what we see in the exponents, these are isotropy group orders. In the case theta equals 0, we have to go to the minimal resolution and take isotropy group orders there. If zeta equals 1, it turns out that the X is necessarily smooth, this elliptic fixed point, and then we can rid off our isotropy group orders from our original surface. So this is the statement on the automorphism group of a rational projective C star surface. The philosophy is that we get it really completely determined by intersection numbers of suitable invariant curves and some isotropy orders of suitable invariant curves. So this is a complete description of the automorphism group. Let us discuss this a little bit. When Timo and I were computing this presentation, somewhere when we have been almost done, there appeared papers by Vanya Cheltsov and Yuri Prohorov, and also by Mast and Stadelmeier, answering some very similar problem. First, they gave all Gorenstein log Del-Pezzo surfaces with an infinite automorphism group. And second, in this situation, they determined the automorphism groups explicitly. "50 out of the 53 listed X," that means Gorenstein log Del-Pezzo surfaces with infinite automorphism groups, are in fact C star surfaces. And for the two of us, it was a big relief to see that the descriptions of the automorphism group indeed coincides with our theorem. An application. I'm interested in almost homogeneous surfaces. That means surfaces that admit a group action having an open orbit. They're also called almost transitive group actions. So 3 equivalent statements. The first one is there is an almost transitive algebraic group action. The second is the automorphism group acts almost transitively. That means there is an open orbit. That's maybe not a big thing so far, but we can describe this again in terms of data of the surface. Second characterizing statement is that our X has a quasi-smooth simple elliptic fixed points, say X minus, in one of the following codes. We see one inequality using terms we have just seen before, and this inequality just says that the number rho is bigger than 0. It's a series of inequalities. And the second series of inequalities, similar data, using similar data, it just says that our number zeta equals 1. Now we may ask which types of groups can act with an open orbit on our surface. Here's the answer. If only one of these conditions, series of inequalities, star or double star from above, holds, then our G is a semi-direct product of C and C star with twisting homomorphism phi. And if we are in the situation of 1 star, then we can say what is the twisting homomorphism. It puts phi of t applied to some s is t to the L1 N1 is order of the isotropy group in the curve D1 N1 times s. And we also can say what is the isotropy group of the general point for this almost transitive action of the semi-direct product. G, this is a cyclic group of order L naught N naught. If we are in situation double star, analogous statement holds just with the roles of L0 N0 and L1 N1 switched. If both series of inequalities are valid, then all the groups from the item 4 just discussed show up. And also we have actions of the almost homogeneous actions of the vector group C2. And these are all groups acting in an almost homogeneous manner on X. Again, I should say that the case of Gorenstein-Lock-Del-Pezzo surfaces was known before. This is due to work of Ulrich Derenthal and Daniel Lafren. In 2 papers, they described the almost homogeneous Lock-Del-Pezzo surfaces, Gorenstein-Lock-Del-Pezzo surfaces. Now, in the case of C-star surfaces, theorem 1 and theorem 2, we do not make any assumptions on the singularities. So they are valid in full generality concerning automorphism groups of C-star surfaces. Okay. So I'm going now to tell a little bit on the proof. It is so that these theorems, they have say quite explicit character, and the same applies to the proof. So I will not go into any details. I will just try to tell you what are our methods and what have been the biggest problems during our way to the result. So first, let me present the working environment for the proof. So that is what we use is the Cox-ring-based approach to rational C-star surfaces. So look, in this picture we again have a C-star surface X with above its source. At the bottom we have the sink, and then we have these arms with the curves dij. And what I now need are the orders Lij of the isotropic group of the general point X in Dij. So assume that in the example we have the following: on the left-hand side arm, on the zeros arm, we have isotropic group orders 3 in the first curve and 1 in the second. Then in the middle, say we have isotropic group of order 3, and on the right-hand side we have isotropic group of order 2. Now the task, or what I want to present, is how do I encode this C-star surface in a suitable manner. And the encoding is done in terms of a matrix. If you look at the first column of the matrix, then we see the number 3. This is the isotropic group order of D01. If we look in the second column, we see the number 1, and that's the isotropy order of D02, and so on. The third column tells us about the second arm, isotropy group order 3, and the last column is the second arm. Observe that the first two columns are of the same type. This reflects the fact that these curves come from the same arm. And then below these numbers 3, 1, 3, and 2, we find some other numbers. From these numbers, you can extract the weights of the action tangent. If you look at the action of the tangent space of the isotropic group C star at X, then this action has a certain weight, and this is the class of the number in the bottom row modulo Lij. Okay, now I claim that from this matrix I can reconstruct the surface, and this runs as follows. The first thing is that we try once more to understand this matrix. So if you look at the dotted line between the upper two rows and the third row, just forget about the third row, so project to the first two variables. What we see is a fan of the toric variety of a toric surface, namely the projective plane. The only strange thing is that we don't have -1, -1, 1, 0, 0, 1. We have just some multiples of these vectors. That's what we put in the picture. So at the bottom of this picture, we see the rays of the fan of the projective plane P2. And then now we take the third coordinate to put these fat points into 3 space. They all lie on this kind of abused booklet, these 3 pages directing in different directions. And on each of these half planes, we find the columns of P that represent one arm of the surface. So we see in this picture the 3 arms of the surface. Moreover, we see in the picture a fan in Z3. It has as its maximal cones a cone sigma plus, which is generated by the upper 3 rays. From each of the leaves, I take the upper vector. This gives me a 3-dimensional convex cone. Then I have a 2-dimensional cone in the arm number 0, generated by the 2 vectors living there. And there is a bottom 3-dimensional cone, which I did not put into the picture. It is full enough already. So that means that is a point where geometry comes in. The fan gives us a toric variety. And that's the next step. The toric variety associated with this fan is basically up to some completion the weighted projective space P1323. And our X sits as a surface in this weighted projective space. And this dotted projection downstairs on the left-hand side is what we have seen is a rational Orlik-Waagreich map given by the inclusion of the field of invariant functions. And on the right-hand side, it just comes from this map of fans given by the picture. To make it more concretely, the toric variety of the fan drawn in the picture in the middle gives us an open subset of the weighted projective space. And our X is a hypersurface, and we can give the weighted homogeneous equation explicitly. It's T01 cube, T02, T11 cube, and T21 square. These are exactly the numbers from the matrix, and if you look back into the picture, these are exactly the isotropy, the orders of the involved isotropy groups. So the exponents of the defining equations, they are strongly related to the geometry of X and its action. Moreover, our X is embedded into the toric variety, then this booklet becomes a new meaning. This booklet is the tropical variety of our X. The P1, as I told you, is the curve corresponding to the field of invariant functions. And it sits in the P2, which is dominated by our weighted projective space. And the defining equations are similar as the defining equation of our X. It is a trinomial equation. This is very typical for the situation. And in fact, if you go into computing details, the defining equation of X is the pullback of the simple linear defining equation of the P1. And the good thing in all this construction is that we get for free the Cox ring of the surface X. It is just a polynomial ring in the variables Tij modulo this defining relation. And the grading of this Cox ring is the same as the grading of the Cox ring of the weighted projective space. So that means once we know the Cox ring of the rational surface, we know it complete. So this is a way to see why this matrix P encodes the X and how we can reconstruct it. In the proof of the theorem, we work with this language using these matrices P and working with a Cox ring of X. Let us go back to the 70s, back to the roots. It was also a fascinating decade for toric geometry because it started by the work of de Mazur. And the work of de Mazur was motivated, or he wanted to say something about automorphisms. In the next slide, also some newer roots will occur. They stem from the year 2014 and can be found in work by Ivan Arzantsev, Elaine Hugenberger, and Alvaro Liendo, and myself. Let us begin with the toric case. The aim is to say something about the automorphism group of a complete toric variety. And the idea is to study this automorphism group via his quotient presentation. That means the presentation of a toric variety Z by an open subset of the R space, open subset Z hat by the action of a quasi-torus. And this C to the R is the spectrum of the Cox ring of Z. Cox-ring of Z is a polynomial ring in R variables. Now let sigma be the fan of the toric variety Z and denote the matrix, consider the matrix having as its columns the primitive generators V1 up to Vr of this fan. Then a de Mazur root at one Vi is a linear from U on ZR such that U evaluates at Vi to -1 and it evaluates non-negatively anywhere else. So existence of such a root is a strong condition on the fan. In general, we won't find such roots, but if we have them, it means that all but one ray, in particular, that all but one rays of the fan, they lie in a common half space. Any such root gives immediately rise to an automorphism on C to the R, even a family depending on the parameter S. It sends a given Z to Z plus, and now I take S Zi, where I should say, what do I mean by Zi? I mean the vector of length R having all coordinates 0 and Zi at the ith place. And this is also times Z to the P star U. What is P star U? P is just the transpose of the matrix P, and I apply it to U. What I want to say is that I get an automorphism of CR, and it is given in a fully explicit manner. And these automorphisms induce subgroups of the automorphism group of Z. So they even descend from CR to the toric variety Z. And the statement is, the fact is that the unit component of the automorphism group of Z is generated by the acting torus and these additive root groups coming from the de Mazur roots. One can say more about this, but this is all we need for the moment. So we have generators for the automorphism group of the toric variety. Let us go to the case of a complexity 1 T variety. It's the same idea. If you want to study the automorphism group, we do it in terms of the Cox ring. Now it looks a bit more complicated. First look at the left-hand side. There we mimic exactly the thing from toric geometry. We take the spectrum of the Cox ring, then our X is a quotient of an open subset by a quasi-torus. Now our spectrum of the Cox ring is given by these nice trinomial relations we have just seen. So it is embedded into a C to the R, and this C to the R is the spectrum of the Cox ring of a toric variety. And as seen in the example construction, our X comes embedded into this toric variety. And we hope that our X inherits as much as it can from this toric variety. Now, for computational purposes, I should mention that these two quotient maps we see in the picture, they arise both from this matrix P we have seen already twice. It's always the same type of matrix P. What we define in the case of complexity 1 T varieties are de Mazur P roots. These are linear forms which evaluate to -1 on a given V I1 and also are non-negative on the remaining columns of the matrix P, but the relations are more specific. I don't want to write down them all. These are a lot of conditions. What we need to take at the moment is this. They are all non-negative on any column different from this vi1, and the conditions are a bit more specific. They have to be greater or equal to some, and some of them have to be greater or equal to some entries of the matrix P. In the same way, these De Mazur P roots define automorphism groups. We go the usual way. We associate a suitable homogeneous locally nilpotent derivation delta U with each such De Mazur P root. And then if we apply the exponential map, these homogeneous locally nilpotent derivations give us root groups. That means additive one-parameter groups in the automorphism group of X. And the fact is almost the same. The unit component of the automorphism group of our T variety of complexity 1 is generated by the acting torus T, and the root groups coming from the De Mazur P roots. So it's a full analogy, this statement. This is what we will use for the computation of our automorphism group of the C star surface, which is a particular example of a T variety of complexity 1. For the moment, it looks quite straight what one should do. But as soon as we started computation, there was one of our maybe main difficulty showed up. The first problem is there are in general much more root groups than we need generators. So we have to understand relations among these root groups coming from De Mazur P roots. That's the first problem. Well, we just try to deal with them. And the second problem is that they look quite complicated. They appear not suitable for explicit computations. So it's not as straightforward as it could look like. Let us look at a brief example. I'm not going exactly through this example, but I hope to give an impression what is the right idea. We look at such matrix P, similar to the one before. Here are the entries, and this matrix gives us a C star surface X, again defined by a nice trinomial equation in some weighted projective space. This does not imply that all the C star surfaces live in weighted projective spaces in that way. This holds only for those of Picard number 1. So then let us try to find the De Mazur P roots without knowing what is the definition. I just give you one. It's U equal -1, 0, 1. We can look what does it do with the columns of the matrix. It evaluates to non-negative on the column V01. It evaluates to -1 on V11, so that's what we need. Then it evaluates to 1 on the column V21. For usual De Mazur root, this would be overkill, but for De Mazur P root, this is what we need in this case. It should be larger than the entry L11. So, than the entry L21 in this case, sorry. And at V22, it evaluates non-negatively. That's enough for De Mazur P root. What I just want to stress is that the conditions are a bit sharper than those for usual De Mazur roots. Similar as before, we can go through this process of taking the corresponding locally nilpotent derivation and exponential map, and it, at the end obtains such root group, which in the present case looks a bit more complicated. You see the formula, how we can give it explicitly, but it looks complicated. And if we leave the case of Picard number 1, situation gets worse and worse and worse. And if we have thousands of them and have to compute relations among such groups of automorphisms, you can imagine that this will be a lot of fun. So we get frustrated, and the idea is another one. The first observation is that our U is a de Mazur P root, so it's more specific, but on the other hand, it is also a de Mazur root. It is evaluates to -1 on one of the columns and non-negatively on the other ones. So that means we can look at the corresponding root group on the involved toric variety, this weighted projective space P27113, which hosts our X. And if we look at this subgroup, it looks much nicer than the previous one. The only drawback is this subgroup does not leave our X invariant, so it doesn't help us to find automorphisms of X, at least not immediately. What can we do? In this case, we can study the example and find two further de Mazur roots. They are not de Mazur P roots, but they are de Mazur roots. And with the help of these two de Mazur roots, we can do something. Namely, the root group of our de Mazur P roots on the left-hand side on the equation can be expressed via the root groups, the toric root groups corresponding to the ordinary de Mazur roots in question. That means that we have a way to put our nasty root group into some pieces. These pieces do not leave our X invariant, but we can compute with them. So this is one of the main tricks. Let me slowly come to an end by giving some words about the proof. The most important ingredient is Timo's formula he found. As we have seen in the example, this holds in complete generality for torus actions of complexity 1, even in on rational T varieties of complexity 1, even in arbitrary dimensions. It's not specific for the surface case. What Timo does, give him any de Mazur P root, then he gives you a formula how it is presented via the corresponding root groups in terms of toric root groups. So that means we have a way to put hands on the root groups without these big nasty computations. So this solves problem 2. That it got too nasty to compute with the de Mazur P root groups. Here are the main steps in the proof. The first thing is to establish the case distinction in the theorem, and this has nothing to do with automorphisms. The theorem we show is that for every C-star surface with a quasi-smooth simple elliptic fixed point, we can show that it has no so-called gentle parabolic fixed point curve with non-negative self-intersection, where gentle means that it should have, with at least one of the arms, the intersection point should be smooth. So the non-gentle ones, all the arms intersect our D plus in singularities. And the other thing is that our X cannot have a second quasi-smooth simple elliptic fixed point, which then must be X plus, but this does not exist. So this establishes a case distinction in the beginning. Now the task is to find among these many, many root groups coming from de Mazur P roots suitable systems of generators so that we can work. And these generating root groups give at the end the coordinate lines in this unipotent part of the automorphism group k to 0 semi-direct k to z theta. And in order to figure out such minimal systems of generating root groups, we have to study relations among these root groups, and this heavily relies on Timo's formula. This computation is a major computation heavily relying on this formula. So the next step is maybe what is in common with all the papers working on automorphisms of surfaces is that we have the minimal resolution preserving the automorphism group. In our case, it can be also directly seen. I mean, behind this one can use big theorems about equivariant resolution. But in our case, we can also see from the combinatorics and the description of the roots that the minimal resolution preserves the automorphism group. That's one thing, and we need indeed to follow the way of our generating roots through the whole story in order to get this description. So we end up in X tilde, and then we do some contraction onto a toric surface. It's again root preserving. Some roots may get lost, but those we need, they are preserved. This allows us at the end to follow the way of our automorphism group into X, so that we can study the structure of the automorphism inside the automorphism group of the toric surface. Okay, so these are the main ideas. Thanks a lot for inviting me for listening.
Okay, thanks, Juergen. Okay, and maybe in I can see reactions somehow. Okay, thank you. Any questions?
Yeah, so with Timo's formula, do you have any chance of saying something about C-star threefolds?
This is a good question. We also discussed this question. The problem is that Timo would be the right one, but there's also a big company who has this thought that Timo would be the right one, so he's going to leave us. It will be an open question, and I think it's a reasonable question to enter the threefold case. I expect it to be more involved than the surface case. And even in the surface case, if you look to the paper, at least our computations are some work. But I think if you really want to know it, then it should be doable.
So for the computations, did you use computer algebra programs, or did you like how complex are they?
Yeah, it is not. It is this computation is we want to derive some formula. We check from time to time by maybe some symbolic computations. Are we right here or there? So that's what we do. But no Gröbner basis, nothing like this.
Good. Nice question, Susanna. Thank you, Juergen, for answering. I have strange question. Probably answer is no. Is it possible to get some reasonable classification of Delpezzo with cis direction, not non-Gorenstein? Reasonable. To get just a list.
Yeah, maybe ask Timo.
Okay. And another question.
No. Timo should.
Timo is here. Yeah. Okay.
Timo is here. I think so. The question is, can we give some classification of non-Gorenstein Delpezzo surfaces
with cis direction? Even I can tell you more precise when automorphism group is just cis star.
So there is a possibility to classify such varieties. And we're on it in the surface case with infinite automorphism groups being almost homogeneous, just the cases that Juergen described in the second theorem as well. So there is a paper in progress with a classification result in that manner.
But if the group just cis star, just one dimensional.
So this is the case you are interested in?
For example. Yeah.
Okay. Well, this means that, yeah. This
Okay, I can
means
tell you the basically the background. Why?
some answer to the question first, maybe.
Yeah.
The question is, in some sense, yes, but it means that we have to violate these inequalities from theorem 2. This gives us precisely the cases where we have C star. So unipotent part is trivial. And I would say there should be a lot. I don't know what is expected. If you have no further condition on the singularities, you get a whole universe, exploding universe.
Yeah. This is why I expect the answer to the problem.
What would be reasonable? What would be reasonable conditions on singularities?
Quotient. Yeah.
Yeah. If we go.
Well, any. No condition.
Yeah. I mean, Timo did thus the almost homogeneous case, which is more restrictive, and even there you have explosions.
Okay.
Yes.
We look at Timo, if I got you right, is something like half log terminal, 1/3 log terminal.
1/3 log
So,
terminal.
I don't know. Maybe you remember roughly the numbers.
Yeah, it's around 15,000.
So, I see. So
yeah, for half, or was it?
A 1/3 log terminal.
Okay, I can maybe let me restate my question in the different way, not a question but suggestion. So, for example, if you take a toric one, and you also put the index, you consider index of Gorenstein index, yeah.
Yeah. Okay.
Gorenstein 2, 3, and you just take the numbers, how many toric you have. I mean, you see it's like explodes, yeah. But if you, on top of this, if you add this condition, for example, that barycenter is 0, you get flat relatively. If you just run a program and you see that number of polytopes, you're going to get, for every index, going to be roughly the same. Not so it doesn't grow. It's still going to be infinite list, but it doesn't grow so fast. But barycenter condition, this is what is like called this K polystable. Barycenter is 0. So, but it's completely explored in for toric. But for C-star surfaces, if you have Delpezza with C-star action, if you put additional restriction that they K polystable, which basically means they have some this Keller-Einstein metric orbital, then this should impose very tough restrictions on everything. And this is absolutely open topic. Some of them do are K polystable, some not, but maybe we discuss later.
Something
we open.
Yeah. Something we did not do so far is if the barycenter of what you mean, the describing polytope.
Yeah. This is for toric.
For toric, we have a replacement. We have a replacement in the Delpezzo case of this polytope, which is called anti-canonical complex. Never thought about possible barycenters, but maybe this is the right way to look.
Yeah. And also the group, automorphism group should be reductive. So you should only have C-star. All other things should disappear.
Okay, yeah.
Okay, any other questions? Juergen, do you have question?
Yeah, it's maybe a strange question. How about three-dimensional case? Suppose
three-dimensional?
We want to classify Fana threefolds with just terminal singularities and C-star action. Is it doable?
So you mean we are in the setting of complexity 2?
Yes. Is it doable?
Yes. The first answer part of
this case,
that's
finite number of families. It's known. In
finiteness.
General.
But what I can say is that higher complexity torus action, complexity 1 is quite, I would say, is close to toric, but the next step is passing from curves to surfaces, so it gets more complicated. Nevertheless, if we do some impose some conditions on the quotient surface, let it be nice, some P2, some P1 times P1 and so on, then things get more concrete. And in the situations that we have a P2, there are these so-called general arrangement varieties. And in this case, there are first classifications also using combinatorial tools coming from the C star action. In this case, we also know about the anti-canonical complex. And the statement with this anti-canonical complex is that it is terminal if and only if you have the lattice points only those vertices as before. So they are the same statements as in the toric case. This reduces the concrete classification to the question of building these complexes with prescribed lattice point properties. So the answer is yes, we are on this, but it seems to be a broad field if you really want to get some concretely.
So it's doable, I see.
Yeah, progress is possible. It's interesting how far we can go. So the funny thing is that in the case of very specific equation, which is in complexity 2 with a generic quotient P2, still they look like this trinomial but quadrinomial. There all the methods work. And if we take a very general equation, so non-degenerate embedding, there the methods work as well. And in between, this is the hell. If you go to the extremes, then life gets easy, but in the middle, it's so difficult. And we try to approach from both sides.
Sounds good.
Thanks.
Thank you, Juergen. Thank you, Juergen H. Vanya, do you have some question? No?
Unfortunately, I was able to join just at the end, so unfortunately, no questions.
Okay. Anyway, it was good to see you. Yeah, and let's then thank Juergen again.
Thank you for listening.
Okay, thank you very much. And I'll upload the video later on the webpage of the seminar. Juergen, thank you. And we will discuss a bit later what I asked.
Yeah, okay.
Okay, good. See you everyone. Bye.
Bye-bye.